Yay. So here we go. We're starting. Have you been noticing that we're essentially taking everything from linear land and we're transferring it to rotation land? Yeah. So for example, in linear land, we've got displacement, velocity, and acceleration. And rotation land, we've got angular displacement, angular velocity, and angular acceleration. In linear land, we have force. Tell me, what is the, what do you call, the counterpart of force in rotation land?
Torque.
Yeah, torque, right? Torque. Okay, well today we're going to take F equals ma, which is what we learn in linear land, and we're going to take the, what do you call, the counterpart in rotation land. Torque equals rotational mass times alpha, and that's what we're going to do. So most of this period is going to be talking about rotational mass, because we've already learned about torque and we've already learned about angular acceleration. The thing you haven't learned about is rotational mass, or I. So that's what we're going to learn about now. So here we go. In linear land, we got F equals ma. In rotation land, we got torque equals rotational mass. Times alpha. You guys okay with that? Instead of mass, it's rotational mass. At this point, you can start working with this formula. Here, let me give you an example. Here comes example number one. A 45 Newton meter torque is exerted on a rotating disc. Its angular acceleration is equal to 3 radians per second squared. Find the rotational mass. Good luck. I'll give you a hint. Please use this formula. Boy, that hum is very loud. Alrighty, well, obviously everyone's getting a 15 here, rotational mass. My issue is the units. Sure, it's 15. Tell me, what's the units of rotational mass? Well, newtons times meters times seconds squared divided by radians, right? Newton, meters, seconds squared over radians, except what are the units of radians? Say again, Gavin?
None.
Yeah, there are none, or there is none, because radians are just a ratio. You know, S over R, the ratio of two lengths is what gives you radians, so radians is unitless. So I don't need the radians, so there we go. That's my unit, so rotational mass has the units of Newton meters times seconds squared. But we can actually simplify this. Instead of calling it Newton meters seconds squared, we can turn our newtons into kilogram meters over seconds squared times meters times seconds squared. And now you'll notice the seconds squareds cancel, and I get kilogram meter squared. And yes sirree, that's the units of rotational mass. Kilogram meter second squared. Kilogram meter squared. Okay, great. Well, let's talk more about rotational mass, okay? Now, first of all, mass is the quantitative measure of an object's inertia, right? So rotational mass is going to be the same sort of thing. So there's actually another name for rotational mass. We call it rotational inertia. Rotational inertia is another name for rotational mass because mass measures inertia. So we call it rotational inertia. There's another name for rotational mass. It's called moment of inertia. The reason it's called a moment of inertia is because a synonym for torque is a moment. When you exert a torque, you exert a moment. So that a synonym for lever arm is moment arm, okay? But we're not using this in this high school class that much, but I just want you to know that moment of inertia is another way of expressing rotational mass. Well, since two of these three names have inertia in it, which starts with the letter I, we tend to call rotational inertia or moment of inertia by the letter I. So let's go ahead and get a nice definition for rotational inertia or rotational mass. Rotational inertia, which we call I, is the following. Remember how inertia was an object's tendency to resist changes in its linear motion? Rotational inertia is going to be an object's tendency to resist changes in its rotational motion. And there we go. An object's tendency to resist changes in its rotational motion. If I can put this in more layman's terms, the bigger the rotational inertia of something is, the harder it is to rotate it, to start it rotating, let's say, or the harder it is to make it stop rotating. Bigger I implies harder to start or stop its rotation.
Can you pop your head in?
Oh.
Not focus, thank you.
Okay. I'm glad I fulfill that purpose. That's like my biggest purpose in teaching the lesson is just to provide a way for the camera to focus. Everything else is like irrelevant. Okay, so rotational inertia actually depends on two things. Mass, linear mass, only depends on one thing, how much matter it has. The more matter something has, the bigger its mass, right? But rotational inertia depends on two things. Here's the first thing. I have a hammer. I'm going to rotate this hammer back and forth like a windshield wiper blade, okay? And so it's going to go clockwise, counterclockwise, clockwise, counterclockwise. I'll be changing its rotational state. You see how I'm doing that? Changing its rotational state, okay? And it's pretty easy. You can tell I'm changing the rotational state pretty quickly. Clockwise, counterclockwise, clockwise, counterclockwise. Okay, great. But is there some way for me to hold this hammer so that when I try to do the windshield wiper blade thing, it would be a lot harder for me to change it from clockwise, counterclockwise? Say again?
Hold it by the handle.
Sure, hold it by the handle. Now, watch this. Now it's a lot harder for me, okay? Before, I was able to do it really fast. Now, I'm not able to go so fast. I can't make those changes so quickly. And tell me, what's the difference? What's the difference between this and this? It's the same hammer.
Rotational mass.
Okay, tell me more. Gavin said the rotational mass. Yeah, in fact, tell me, based on what I've been telling you, where do I have more rotational mass? Like this or like this? Which has more rotational mass, this way or this way? How many people vote this has more rotational mass? Okay, good for you guys, because it's harder for me to rotate, so it's got more rotational inertia. Well, tell me, what is it about the hammer that makes it harder for me to do this than to do that?
The mass is farther away.
Thank you. The mass is farther away from what point?
Rotation.
Yeah, the point of rotation. You guys okay with that? So that's the first thing rotational inertia depends on, how the mass is distributed. Okay? Rotational inertia depends on how the mass is distributed. If mass is far from point of rotation, I is big. Now I'm going to use a different color for the next one. If mass is far from point of rotation, I is big. If mass is close to point of rotation, I is small. So yeah, how the mass is distributed is very important. It determines what your rotational inertia is. I have a few demonstrations that demonstrate this idea. Here's one demonstration, this idea of balancing this incredibly tall stick on one finger. I'm going to try to balance it now. Here we go. Okay, wait. I'm going to balance it now. Here we go. Oh, okay. I'm finding it very difficult to balance this stick, okay? But now I'm going to take a 2.2 pound weight, I'm going to put a 1 kilogram mass, and stick it on the end. What have I just done to the rotational inertia of this object? Yeah, I increased it, right? I made it huge. Because now I put a gigantic mass incredibly far from the point of rotation. Because this guy, it wasn't falling out of my hands, right? It wasn't falling straight down. This guy was rotating out of my hands. See what I mean? So by putting this heavy mass here, I've greatly increased the rotational inertia of this system. And so now tell me, is it going to be easier or harder for this thing to rotate? Go ahead, Noel. Yeah, harder, way harder. Whereas before, let me just take this thing off. Okay, before, it was incredibly easy. I hold it for 1 second, I go boop, and it go boop. It was just rotating out of my hand really easily. But now that I'm going to greatly increase the rotational inertia, I should be able to balance it more easily. Now, of course, my goal is to not have this actually fall on any of you, because that would be really bad for my career. Here we go. Would you say this is easier or harder?
Easier.
Yeah, way easier. Look, I'm not even moving my feet. This is way easier because it's a lot harder to rotate because it's got so much more rotational inertia. And so it takes forever for it to start rotating. By then I can adjust. You see what I mean? So this is very easy. Now, I used to let students do this, but sometimes I get students who are kind of spazzy and so it'd fall on someone, and I just couldn't do that anymore.
Let Stanley do it. Let Stanley do it.
Let's not. But maybe join us if he wants to. Okay? Here, let me give you another example of increasing how you're, increasing the distribution of mass far from the point of rotation, making it harder for something to rotate. What if you're walking on a railroad track? How many people have walked on a railroad track? Okay, many of you. How many people are afraid to because you're afraid you get run over by a train? Get serious. You would hear it way before it ever hit you, so don't even worry about it. Stop being afraid. Okay, so I'm walking along a railroad track, and tell me, what do I do with my arms? Where do I put them? I put them out to the side, right? Because what am I doing to the rotational inertia of my body when I put my arms out to the side? Yeah, I'm increasing it. I'm distributing a bunch of mass far from the point of rotation. You know, it would be even better if not only if I put my arms out, but I was holding a bowling ball in each hand. Then, man, then I could walk those rails easy as you please with a bowling ball in each hand, because now it'd be very hard for me to rotate off of that rail. See what I mean? Yeah. Hey, let me give you one more example. The simple pendulum. Tell me, what's the point of rotation for this pendulum? Yeah, right there, right? Where my fingers are. Okay, so right now the mass is very far from the point of rotation, but what if I cut the string in half? What would happen to its rotational rate, its radians per second, its angular velocity? Yeah, here, watch this. Boop. Do you see, doesn't that seem like a higher rotational rate than this? You know? Or how about if I, went like this? Or this? See what I mean? And so by reducing the moment of inertia, by distributing the mass increasingly closer to the point of rotation, I'm able to make it easier for it to change its rotational state. Yeah. Now, there's one more thing that rotational inertia depends on. And I'd like to demonstrate it right now. I'm going to do my windshield wiper thing with this hammer and this hammer. And I want you to see right now, because of where I'm holding the hammers, the distribution of the mass is the same. All of this mass is distributed far from the point of rotation. All of this mass is distributed far from the point of rotation. You see that? But tell me, which of these has the greater rotational inertia? How many people say this has the greater rotational inertia? Here, let's find out. Remember this guy, I can do my windshield wiper about like this. This guy, much slower. Why does this guy have more rotational inertia than this? Their masses are distributed identically. What's the difference? Someone tell me. What's the difference between this hammer and this hammer? Which hammer would you rather get hit by? Why? Why not this one? What's that? Okay, but what is it about this hammer that's going to make it hurt more?
It's going to bounce.
Yeah, say again, Alejandro.
Oh, more mass.
Yeah, more mass. Whoever said it, thank you. More mass. So I need to make sure you're aware, rotational inertia also depends on mass, right? This has way more mass than this guy. And so he's going to be harder to rotate, all things being equal. So that's the second thing that it depends on. Not just how the mass is distributed, but the mass. It depends on the mass. All things being equal, something with more mass is going to have more rotational inertia. Well, on page 253, you've got a list of common objects and what the formulas for their rotational inertia is. So one example is if you have a point, so this is page 253, let me write that down. List of eyes is on page 253. So it turns out that if I have a point mass, some mass m, that's some distance away from a point of rotation, and this mass m is rotating round and around, like the pendulum I was showing you, it turns out that the formula for this is mr squared. That's the formula for the rotational inertia of a point mass rotating a distance r away from a point of rotation, a radius r. And by the way, do you notice these units are kilogram meter squared, just as we found in our very first example? Well, now that you've got a formula for rotational inertia, let's go ahead and do a problem. Hey, example 2. A 2 kilogram ball is on a 1.5 meter string. And has acceleration, angular acceleration, of alpha equals 3 radians per second squared. Find the torque. How much torque must be being exerted on this system so that it can have that angular acceleration? And I'll give you a hint. Please use the formula torque equals I alpha. And for I, please use this because that's what I'm describing. Good luck.
I'm gonna fight you and I'm gonna win. I'm Hamlet. I'm gonna fight him and I'm gonna win. See? If 1G and Hamlet fights, if 1G.
So what number are you guys getting? Guys getting 13.5? Good. 1.5 squared is 2.25, twice that 4.5, 4.5 times 3 is 13.5. And the units end up being kilogram meters squared over second squared. But you know that kilogram meters per second squared is newtons, and so I get 13.5 Newton meters, which is just what you would have expected for torque. So here's my next question. I've got 2 objects with identical radii and identical masses. One is a hoop, the other is a disk. Hoop. I'm not able to make a very good hoop. Disk. Oops. It's got to have the same radius. Tell me, who has the bigger rotational inertia? Who has the bigger moment of inertia, the hoop or the disk? They have the same radius, they have the same mass. You ready to vote? Who's got the bigger rotational mass? How many people say the hoop has the bigger rotational inertia? 1 of you, 2 of you. How many people say the disk? Okay, many of you. Okay, let me just remind you, how should the mass be distributed from the point of rotation? And by the way, if my hoop is rolling or my disk is rolling, where's the point of rotation? Yeah, in the middle, right? I mean, if my hoop or my disk is rolling, then the point of rotation is going to be at the middle. And I want to remind you, big rotational inertia means that the mass is distributed far from the point of rotation. So you're always going to ask yourself, which of these guys has most of its mass distributed as far from the point of rotation as possible? So only about 7 people voted. So now think, which of these 2 guys has its mass distributed far from the point of rotation? Whoever that guy is, he's going to have the bigger rotational inertia. How many people choose the hoop? Okay, good. So Justin's no longer a voice crying in the wilderness. Lots of people joined it. How many people still go with the disc even though it's totally wrong? Okay, good. All right. Well, if you look in the book, the rotational inertia of a hoop is mr squared. That is, a hoop is no different from a point mass. It's just a collection of point masses. And the rotational inertia of a disk is 1/2 mr squared. So let me ask you this question. Suppose I have a race. I'm going to have the hoop and the disc go down this ramp. And I'll put this hammer here to stop them. Tell me, who's going to win the race? The hoop or the disc? How many people say the hoop? How many people say the disc? Okay. Well, someone tell me, why? Why do you choose the one you choose? Yeah, Gavin.
The disc, in my mind, should win because it's able to rotate more times since it has a lower rotational inertia.
Okay. You guys hear what Gavin says? He thinks the disc is going to win because it's easier to rotate. It's going to rotate more times because it's got the lower rotational inertia. Whoever voted for hoop, why the hoop? How many people then agree with Gavin? How many people were convinced by Gavin? Yeah, you're un-American. You got convinced by reason. Hey, let's go for it. Or do I really need to do it?
Yes.
Okay. Here we go. Hope it doesn't roll off the thingy. 1, 2, 3, Who was winning before it fell off? The disc, right? Hey, let's do that again. Let's see if I can get the disc to do the whole track. I've got a shim under here. Let me press that shim down. Okay, great. We'll try this one more time. Okay, happy disc. Oh, the disc went off the left, didn't it? Off the right. Okay, here we go. Woo. Okay. So do you agree that the disc wins?
Yeah.
So here's my next question to you. Let's say I had a race between the hoop and a sphere. Who's going to win this race?
Sphere.
Good. Why the sphere? Well, because if is the how's the mass distributed with the sphere?
Similar to the disc.
Yeah, similar to the disc. So now my question to you is this: who wins this race, disc or sphere?
Sphere.
Why sphere?
Its mass is distributed.
Well, let's do it, and then you guys will see from the formulas on page 253. Here we go. 1, 2, 3. So who won? Who won that race? Sphere, barely, but the sphere won. And we'll talk about it more tomorrow because we're almost out of time. But it turns out that the rotational inertia of a sphere is 2/5 mr squared. So it's ever so slightly less than the disk. And so because it has even less rotational inertia, it ended up winning by a little bit.
Just a wee bit.
Where'd my sphere go? Under the thing? Okay. Well, hey guys. So remember, torque equals I alpha. Remember, page 253 has all of your alpha, all of your I's, and you'll just be mindlessly plugging into the formula. So good luck on tonight's homework.